Morning all. Now today I'm going to try charging one of these ultra-fire lithium-ion 18650 batteries using this little lithium battery charging module. And these modules are all over eBay and they're very cheap. This listing is for 2 of these modules and it was only £1.21. Came from Alice 110 1983. Now Alice doesn't sell on eBay UK anymore, so you have to go to ebay.com to buy these, but that prices this little board at 60p. Now I also bought some of these 18650 battery holders, and here's the listing, and it was 4 of them for £1.38. Who was this from? It was from Each Desk, which prices that at about 35p. So for the little charger board and the battery holder we're looking at less than a pound, about 95p. Now this board's pretty amazing. I mean, for that price, to have all the functions of a lithium-ion battery charger is pretty astonishing. It uses this chip, which is a TP4056. There's a few discrete components on there. Couple of LEDs, a red one and a blue one. The red one comes on when it's charging and the blue one comes on when it's finished charging. And then you've got this mini USB. It's the slightly older type USB connector. So the chip requires between 4.5 and 5.5 volts. But of course the easiest way to source that is from a USB charger point. So here's the datasheet for the TP4056, and you can see that it implements a 4-stage charge cycle, including 1/10 of the full current pre-charge, which is this little bit down here. That is until the battery voltage reaches 2.9 volts. Then it goes to a constant current charge while the battery voltage ramps up. When the battery voltage hits 4.2 volts, it goes into the constant voltage charge part of the sequence, where the current starts to fall away, and then when the current drops to 1/10 of its nominal value, which is an amp, the default value, you get the termination of charge and the thing shuts off. So that's 4 sections to that, and this chip handles them all. Now just one thing I should say about this battery holder, and that is that the way that this riveted in positive connection has been implemented, it won't actually work with the flat top batteries, this type on the left here, but it does work with the button top batteries. So I'm going to use this Ultrafire 3000 milliamp hour. It says it is, haha, that's a laugh, it's more like about 600. But that actually is an advantage when charging this, or at least when looking at the charging sequences of this module, because we can actually see in real time the various stages. Now this chip has a programmable charge current, maximum is 1 amp, and the charging current is set by this resistor down here at the bottom. You probably can't see, but it's a 1.2k, and that sets the charge current to 1 amp. By raising the value of that resistor though, you can lower the charging current right down to about 130 milliamps, I think. And here's the table of charging currents depending on what value resistor you use, and as I say, that one at the bottom, 1.2k, gives you a charge current of 1000 milliamps. And they say that you should charge lithium batteries at about half C. Well, C on this cell is 3 amps, so we would charge at 1.5 amps. So I'm going to charge at the default of 1 amp. And there's the system wired up. I've got the lithium cell in its battery holder. I've got the charging board, the TP4056 sitting here. You can see I've soldered a couple of wires on there, and I'll explain what they're for in a moment. And I've got the USB connector connected in, and that's going up to my phone charger, which is plugged into the wall socket. So charging this lithium cell properly and fully is as simple as connecting the little board up to the battery, and the red light's on, so we know it's charging, and when it's fully charged that'll switch to the blue light. But that could be 2-3 hours, and it would be nice to see what's actually going on in this setup, more than just that red light shows us. So I'm going to get the oscilloscope out again. So I've connected the oscilloscope directly across the battery connections, and that means I can monitor the battery voltage, and you can see there that it's 4 divisions above the minimum. The minimum is here, that's the 0 point, and we're up at about 4.2 volts. And if I look at the Vmax for channel 1 there, it says 4.16 volts. So this is in the constant voltage phase of the charging. But it would be nice to monitor the current as well, and you can do that. I've connected the second oscilloscope probe to pin 2 of the chip, and if we look at the data sheet, pin 2 prog there is the constant charge current setting and charge current monitor pin, so you can actually watch the current that's being fed to the battery on that pin. So you can see there where I connected the yellow probe, and it's showing current. It's actually showing a voltage, but there's a one-to-one relationship between current and voltage, so you can just read that as current. And we're 5 divisions up when we started, and I've got, what have I got, 100 millivolts per division. So it started charging at about 500 milliamps, and you can see that that charge current is starting to reduce. So we are in the constant voltage phase of charging. The constant current bit we missed, and the current's dropping away ever so slowly. So looking at this graph again, we are here where the voltage on the battery is held constant at 4.2 volts, and the current is starting to drop away. Now I want to see the constant current section, which precedes the constant voltage section. So I've got another of these ultrafire red batteries connected up to a light bulb, and I'm just discharging it, and I'm going to wait until that bulb starts to go dim. Then I'll put that battery into this charging setup, and hopefully we'll see on the scope the constant current section. So that bulb's pretty dim. I've had to put 2 bulbs on to flatten the battery in a reasonable space of time. So let's take that battery out and put it in the charger. Okay. So I've set this to 20 seconds per division. Now that looks like the pre-charge phase because we've got a very low current there. The battery voltage is coming up, and there goes the current to the much higher current of 1 amp. I'm on 200 milliamps per division there. The battery voltage is moving up, but that is the constant current phase of 1 amp. And then when that battery voltage reaches 4.2 volts, which is the next dotted line above it, it will switch to the constant voltage phase, and that current graph should start sloping down. I'll come back when it reaches that. Now the voltage has got close to 4 volts, and actually the current has started to drop now, and that's a bit like the graph here where you've got this stage of the voltage coming up to 4.2 volts and the current starting to drop away. But it's going to wrap round on my screen now any minute now, and I'm going to lose that pre-charge section. Right, it's wiped that out now. But I'll keep filming this right until the end of the charge sequence, obviously not the whole thing, so that we can see the full constant voltage phase as the current starts to drop away, and I'll slow down the time base as well. So there's the first screen full of data. I'm on 100 seconds per division, so that represents about 16.6 minutes. The voltage has maxed out. It says that it's 4.08, so about 4.1 volts, but I'm not sure how precise my oscilloscope is. And the current has got down to about, well, it's getting down to about 600 milliamps. And you can probably see now why I said that having a rubbish battery that holds very little charge is an advantage, because this is all happening so much more quickly. So about 30 minutes in now, the current has dropped to nearly 400 milliamps, voltage still constant at 4.1 volts. Now the charge won't terminate until that current drops to 100 milliamps, which is when the little light will go from red to blue. So it's now about an hour into the charge, and it's dropped to about 250 milliamps, but I'm starting to think that there is a side effect of using these rubbish batteries, and that is that they have a very high internal resistance. So it's spent literally a couple of minutes in the constant current 1 amp charge phase, and now it's been an hour in the constant voltage charge, but of course it's charging at a much lower current now, about 250 milliamps at the moment. And so I suspect that with a decent battery with a very much lower internal resistance, it would actually charge, or it would put more charge into the battery in much less time. So I'm going to get myself some decent batteries, I think. And so there it is. After about an hour and a half, the red light has changed to a blue light, and on the scope you can see that the current, the yellow trace, has dropped down to 0, so there's no longer any current going into the battery. You can also see on the red trace that the battery's terminal voltage, the voltage across the terminals, has dropped down ever so slightly, and that's because lithium batteries are not trickle charged. When the charge is completed, the charger simply switches off, and that's it. So a final look at this charge graph. Charging these rubbishy ultra-fire batteries, the constant current phase, we only had a minute or two, and then in the constant voltage phase there was a full hour and a half. And the problem with that is that we had very little of the high current charge and lots of this much lower current charge. So it took a long time to charge these ultra-fire batteries. So it'll be very interesting to see whether, if I use some decent batteries, whether the whole process will be much more efficient.